In this video, we're going to talk about ratios, rates, and scaling. So let's start with some examples before we kind of say what ratios and rates are. But there's actually a book called Ratio by Michael Ruhlman, and he states in there that bread is made up of 5 parts flour to 3 parts water, and that's a weight comparison. A lot of baking is done by weight. So let's write 3 ratios that would be equivalent to a 5/3 ratio of flour to water. Let's do a small batch, maybe a large batch, and let's include units. Okay, so since this is by weight, a small batch would be like grams, 5 grams of flour to 3 grams of water. So let me just kind of make a note here. The flour's up top, water is here. All right. So that's one comparison or unit of measurement. We could do ounces, 5 ounces compared to 3 ounces. Or if I was a bakery, maybe 5 pounds compared to 3 pounds. And maybe more. But there's the idea. We could have written this with any weight measurement, but what's interesting is that we're talking about the same weight for both amounts, for both the flour and the water. Okay, so suppose we read somewhere that standard bread uses plain flour as 60% hydration. That means it's a ratio of water to flour weight. So 60% hydration. So it's like 60% hydrated. The bread is 60% hydrated. Okay. So how does this compare to Ruhlman? So let's kind of make sense of this. When we're talking about percentages, percentages are out of 100. So they're talking about a 60 out of 100. But for their comparison, they're comparing water to flour. So they're actually doing it in reverse. Okay, so let's see how this compares to Ruhlman. Let's reduce this fraction. I can divide, let's do it by 10 first. I don't have to, I could go bigger than that. So 60 divided by 10 is 6, 100 divided by 10 is 10, and I can divide that by 20. I'm sorry, 2. I was thinking in my head that I could have, if I wanted to, just divided by 20 to begin with. 20 goes into both 60 and 100, but that's okay. I did it in steps. This is reduces to 3, 5. And again, it's a weight. So it's some units. It could be 3 grams to 5 grams. But what's interesting is this is the same thing as Ruhlman. It's just written in reverse order. They have the water first, flour second. So how does this compare? They are the same. Just written in reverse. So he does a comparison with the 5 to 3, but this one could be written 3 to 5. These are the exact same thing. They're the same. Okay, cool. So that's what the difference is in those two statements. Let's look at another example you might have seen in life, debt to income ratio. And if you haven't seen this in life, you may want to check it out. It's pretty interesting, but it's the idea that you want to keep a certain amount of money owed, like by loans, in a certain ratio of your income, your monthly income. So let's look at that by example. Let's say a student, so somebody's going to school, has a mortgage payment of, sorry, I just want to make sure I had the whole sentence, a mortgage payment of $700, card payment of 125, and some $175 in other loan payments, maybe a credit card or something, who knows. Okay, let's write their, oh, I'm sorry, they mentioned their gross income, that's their income before taxes, of $2,500 per month. What is their debt to income ratio? Okay, so we're going to do debt in the numerator, income in the denominator. Okay, so before I do that, I should probably figure out what their debt is, right? So I'm going to go ahead and add up. So their debt is $700 plus 125 plus 175. And if you can't do that in your head, grab your calculator. But that's going to come out to 1,000. Okay, so this student, their income is 1,000 compared to 2,500. Okay, so we're going to reduce this because it makes more sense when you're comparing to have them reduced. So I can divide top and bottom. I could start with 100, but I'm going to actually use the biggest number possible, 500. 500 goes into both of those. So if I divide 1,000 by 500, that comes out to 2. 2,500, that comes out to 5. Now I'm going to put the dollars, but I'm going to drop it here in a second. So we're saying $2 of debt for every $5 of income. Okay. So the better way of writing that is just 2 over 5. That is this student's debt to income ratio. Or if I wanted, I could use the colon, right? If I wanted to write it like that. Okay, a nurse pays $1,500 a month for her mortgage, 100 for car loan, 400 for other loan payments. Her income is much bigger, $6,000. What is her debt to income ratio? Okay, so for her, let's do her debt really quick. So for her, her debt is 1,500 plus 100 plus 400. So that comes out to 2,000. So using the same debt on top, income on bottom. Here, let me just write it down anyways, just to make sure that we understand that we're using the exact same comparison. Hers is $2,000. That's a 2. $2,000 to $6,000. Reducing, I could divide top and bottom by 2,000. 2,000 actually goes into 6,000. And that reduces down to 1 over 3, which again, I'm going to drop the dollar sign. So $1 of debt for every $3 made. So hers is 1 to 3. Here, I'll just write that as a regular fraction. Oops. Or I could use the colon. So let's look at comparing them. It is a little hard to compare them as is, just because they are a little bit different. One nice way to compare them is to make the nurse's debt kind of similar. In other words, if I were to try to get them somehow to match, like I'll make the numerators match. That means then that she has $2 of debt for every $6 of income. So I multiply top and bottom by 2. That's the comparison. She's $2 debt to $6 of income. He has $2 of debt to $5 of income. So who has the lower debt to income ratio? The nurse does, because she's making an extra dollar every time they have the same amount of debt. So her debt to income ratio is lower than the student's. And I believe that's what they say here. Explain why her debt to income ratio is lower than that of the students. So the explanation is she's making a lot more per month. So the nurse makes a lot more per month. And that causes her debt ratio to be lower. And we're comparing that it's this, she's for every $2 of debt, she makes $6 in income, where the student is $2 of debt, it's $5 of income. So she makes this extra dollar for this debt comparison. Okay, another example, aspect ratio. So this is a comparison of width to height. So let's look at a photograph. Standard photographs are often 10 inches wide by 8 inches high. Let's write that as an aspect ratio. So first, I'm going to write it as 10 inches over 8. I'm not going to write inches anymore. I'm going to drop that, and I am going to reduce this. They are both divisible by 2, which comes out to 5, 4. That is the aspect ratio, or if I wanted, I could do the colon version if I wanted to. We tend to work with the fraction version just because we're used to working with fractions so much in math, it makes sense. But you can write it with the colon if they don't specify. What shape of the photograph has a 1-to-1 aspect ratio? So that's 1 like inch high by 1 inch, I'm sorry, 1 inch wide by 1 inch high. So whatever the unit is, it's a 1 unit by 1 unit. That's a square. If they're equal, that's a square. So we're looking at a square if they're equal. All right. So they kind of sum up ratio as that we can write it in a few different ways. We can write it in words. This is typically how we saw them in the problems. Write it as a fraction, write it with a little colon. We can drop the cups. It just kind of depends on how we want to do it. All right. So let's look at rates. So the difference is up here, ratios are comparing two quantities with the same units, but a rate is comparing them where they are typically different. So 8 pounds per 4 weeks can be written as 8 pounds over 4 weeks. 10.25 per hour can be written as 10.25 over hour. So we can scale these rates and ratios by multiplying or dividing by a common number. And I did that up here when I looked at the nurse's income. So that's called scaling. So 45 miles per hour can be scaled by 4, meaning we times both the numerator and denominator by 4. We get 180 miles traveled in 4 hours, if that's constant. We could do it in steps. They say, show that $15 per 6 years is the same as $10 per 4 years. Okay. So we can show they're the same because $15 per 6 years, if we divide both of those by 3, that gives me to $5 per 2 years. And then if I multiply that by 2, 5 times 2 is 10, 2 times 2 is 4. So boom, this is the same as this, even though you maybe don't think they were the same. They are. If we scale appropriately, we could divide first and then multiply so that we could show that they are the same. Okay, so let's do some scaling. They mentioned something called unit rates, which they'll define in just a minute. But let's go ahead and look at how we could do some scaling here. So it's recommended weight loss at a rate of 8 pounds per 4 weeks. So they say, write that as a fraction and give 2 different rates that are in fact equivalent to saying this. Okay, so 8 pounds per 4 weeks. So I'm going to write 8 pounds and I'm going to use LBS for pounds over 4 weeks. Okay, so one equivalent fraction. Let's say I divided top and bottom by 4. So that would be 2 pounds for 1 week. That's a nice way of thinking of it. So for every week losing 2 pounds, that's a good recommended weight loss rate. Okay. Another equivalent fraction would be, let's say I scale up this time. Let's say I take that 8 pounds and 4 weeks, and this time I multiply instead of divide. Let's say I multiply it by 2. So that would be 16 pounds in 8 weeks. All right. Scale 10.25 over an hour and give 2 other rates. So when you don't see something in the numerator denominator like this, like it's technically implying 1 hour. So this is 10.25 over 1 hour. Here, I'm going to abbreviate hour. So let's scale it to 2 other rates. Let's go ahead and multiply and see what happens when we double it. We'll just start nice. Doubling it would give us, that would be 2050 for 2 hours. Okay. Let's pretend this is like a wage then. Let's do it by 4. Let's multiply 10.25 by 4. So here I'm going to be a little bit lazy and I'm going to just indicate, oh, wow, that I'm timesing it by 4 this time. timesing both top and bottom by 4. So I'm looking at the original here. So 1025 times 4, let's see, that should be 41. And again, use your calculator if you're not sure. I chose 4 on purpose though, because I knew that 25 cents, 4 of them is going to add up to $1. So that was going to get rid of the decimal. So that's going to be 41 for 4 hours. So $41 every 4 hours. So there's 2 equivalent rates. So what's the difference between ratio and rate in your own words? Okay, so in my own words, I kind of think of it like this, and you could say it differently if you'd like. This is up to you. For me, a ratio compares like units. But a rate compares different units. Sorry, that looked like a sad R. Compares different units. That's how I'm going to say that. A unit rate is when we have a denominator of 1, like the 1025 per hour. That's an example of a unit rate. Or 45 miles per hour, or 2.5 hours of TV per day, or a pay rate of $12 per hour. All of those, and you see they put the parentheses of 1, are implying that it's 1 hour, 1 day. That's the implication. So that is useful when we're doing some comparing again. So Jasper earned $100 for 8 hours of work. Jermail earned $100 for 5 hours. Write each rate as a fraction, then find the hourly pay rate. So hourly pay rate is the pay per hour. Or per 1 hour. So they're basically wanting us to get it down to a unit rate. Okay, so here's how we could do it. Let's start with Jasper. So Jasper does $100 for 8 hours. So in order to get it to 1 hour, I need to divide top and bottom by 8, because that's going to get the denominator to be a 1. And that's what I want, 1 hour. Grab your calculator if you need. Oops, sorry. I'll do 1 hour. 100 divided by 8 comes out to $12.50. Sorry, my dog is making noise. $12.50 per hour. So that's Jasper's hourly rate. Okay, so let's compare that to Jermail. I'm hoping I'm saying that right. That's $100 for 5 hours. So this time I'm going to divide by 5 because I want to get that denominator to be a 1. So that's 1 hour, and 100 divided by 5 is 20. So Jermail makes $20 per hour. So that is the comparison of their 2 pay rates. Now scale up to find out how much Jasper and Jermail would make for 12 hours of work. So we're going to take those unit rates and we're going to multiply it by 12. So starting with Jasper. Okay, so his $12.50 per hour. If I want to figure out how much he makes in 12 hours, then just times it by 12. So that comes out to $150. So he's going to make $150 in 12 hours. Okay, so Jermail his $20 per hour. I'm going to multiply again by 12. And that's going to give me $240 in 12 hours. So that's how much they would make in 12 hours. All right. In the period from 1964 to 2014, about 1,140 gigatons of carbon dioxide were released into the atmosphere. Use scaling to find 3 weights that are equivalent to 1,140 per 50 years, because that's a 50-year period. Per 50 years, include a unit rate. Okay, so let's look at this. three rates that are equivalent to this. Okay, so let's start with 1140 gigatons for 50 years. Okay, so let's do a unit rate. So the unit rate would mean I'm dividing by 50. So 1140 divided by 50, doing that on my calculator, that came out to 22.8 gigatons per year. All right. Let's see how much space I have. Okay, so since I don't have a lot of space, let's scale up. Let's scale up to let's double it. Actually, here, we can scale up the unit rate. Nice. Let's do that. That way we can do it a little bit quicker. So let's scale up 2 by 2. And that gives me 22.8 times 2. 45.6, oops, 45.6 gigatons in 2 years. And I could play this game as long as I want. I could scale up from the original or from the unit rate, whichever one I want. I'm going to go ahead and leave these 3 as the rates, even though they may have actually wanted a third one, just because of space. That's fine. This is the original. I will pretend that that works. All right. So according to our 3 number statements, now we haven't talked about 3 number statements. This was some worksheet that they created and we did not use. What we're going to get from that information is the world needs to limit carbon dioxide emissions to 565 gigatons over 38 years. So you scaling to figure out what the annual carbon dioxide emissions per year need to be. So they're telling us per year, that's a unit rate. So they want us to figure out the unit rate. And they tell us to round our answer to the nearest 100. So if it's 565 gigatons for 38 years, the unit rate, we're just going to divide by 38. So in my calculator, oops, 565 divided by 38, I'm going to get 14.86842105. Okay, which I want to round to the nearest hundredth. So that means here, I'm going to write it out, 14.86842105, and keeps going. Okay, but the nearest hundredth for us, this is in the hundredths place. So looking at the number next to that, it's going to round up. So this would round to 14.87 gigatons per year. I could have, by the way, wrote that a little bit quicker, 14.87 gigatons. Wow, gigatons per year. I don't need to write the per, sorry, per year. This would be a shorthand way of writing it without writing it as a fraction. All right. So based on our past information, 2014 to 2016, the emissions were 36 gigatons per year. If we continue this pattern for 33 years, how much carbon dioxide would we emit? Okay, so if the pattern is 36 gigatons, oops, gigatons per 1 year, for 33 years, I'm going to scale up by 33. All right, so on my calculator, 36 times 33, I am getting 1188 gigatons for 33 years, which is no good compared to the information we just saw above. If that's supposed to stay at 565 for 38 years, like we're already like overseeing it. Sorry, the screen's like wigging out because I'm moving it and it's having trouble keeping track of what I was writing. So here's some more real life rates: heart rate, speed, fuel economy. Let's give an example of a unit rate that's different, maybe using something from our life. Okay, so let's say you make, I don't, somebody makes $15 per hour. That sounds reasonable. That would be unit rate. Now, since I'm not going to see your paper, you could write whatever it is you make per hour, but that could be an example of a unit rate. There's other examples you could talk about, like your heart rate, right? Or something along those lines. But there you go. That's how we could do. Okay, if you travel 45 miles per hour, how far will you travel in 4 hours? Write your answer as a rate. Describe in words how you found your answer. Okay, so 45 miles 45 miles per hour. So 45 miles per 1 hour, and we'd like to travel for 4 hours. So we're scaling the denominator, making it a 4. So we're multiplying top and bottom by 4. Grabbing my calculator, and I believe they did this earlier in that example of scaling. They did 180 miles for 4 hours. So this is the rate. And how I found my answer, I scaled by multiplying by 4. If your vehicle has a fuel economy of 32 miles per gallon, how many gallons will you use to travel 16 miles? Write it as a rate. So 32 miles per gallon. So per 1 gallon. Here, I'll use some shorthand here just to make my life a little bit nicer. 32 mi for 1 gal. Okay. So we want to do 16 miles. So to get 16 miles, we're going to divide 32 by 2. That gives us 16. But dividing 1 by 2, that's a half. So basically, it's 16 miles for a half a gallon. So how did we do it? We scaled this time by dividing by 2. And I went ahead and wrote the denominator as a decimal because that made sense. I could have wrote 1/2, like 1/2. That wouldn't have been terrible. But I typically, when I'm writing fractions, I typically like to switch to decimals then instead of having fractions in a fraction. Okay. If incomes are increasing $15 every 6 years, how long would it take for incomes to increase to $35? So if we want to figure out 35, that's a little bit more challenging because there's nothing I can multiply 5 by to make it 35. But I do notice that 15 and 6, they are reducible here. I'm going to switch that to the abbreviation years. Okay. I can reduce these, make it smaller. I can divide both of these numbers by 3. Maybe that'll make my life a little bit better. That's a 3. Sorry. Fix that. Okay, so 15 divided by 3 is $5. And that's 2 years. Okay. Okay, now I can turn 5 into 35 by multiplying it by 7. Boom. So $35, it's going to take 14 years. So this time we scaled twice. First, we divided by 3, then multiplied by 7. So what's the benefit of using a unit rate? The benefit is it's good for comparing. But it's also easier for scaling. So like this last example, if I had been working with a unit rate, that would have been a lot easier. If I had been working with like the unit rate for 15 over 6, by the way, if I divided that, is 2.5, I could have figured that out a little bit easier, rather than working with the original numbers that we kind of did. So it's nicer for scaling. Like you might remember earlier when we were scaling these, right? It was just so much easier when we started with a unit rate. So it's easier for scaling and it's good for comparing. And there you go. Rates and ratios.